Yeah. Okay, so basically what we went over are a really long lecture. I apologize for this. We actually put two lectures together to make this one of all of the linear classification models. And linear classifiers are extremely important because without linear classifiers, basically the rest of the more complicated ones don't work. They're all, many of them are variations on the very simple linear classification model. All of the, you know, the neural models, which are basically those types where you're layering things on top of each other. We're going to start with the perceptron. So I think you guys are all pretty familiar with it. Okay, so basically when we have linear models, we're just looking for a simple hyperplane to separate a binary class, a positive from negative points, right? And then when we have nonlinear mappings, then we can get a curvy space like this. You'll see this a little bit more in SVMs this week, although we don't go into the math for that because, you know, while it's interesting, it's actually not that helpful in real life. Okay, so just to understand the idea of the SVM is good. Okay, so basically, again, we have a signal. The signal is just basically denoted as S. It's the multiplication of a set of weights, sigma, theta, times X, right? Our X is some observation. It could be a scalar, all right? Or it could be a vector of scalars, right? That's usually what we think of is like we have an X, a data row, okay? And that data row is going to be written as a long vector row, right? So we can just say, let's see, do I want to use the ones in this? Okay, we'll try. Okay, something like this, right? So we have a bunch of x's, x1 through n for the nth one, right? And we have, with associated with each of these guys, a weight, right? A sigma 1, a sigma n. And in many cases, we still need a bias, right? The bias is going to help us get the hyperplane off of the origin, right? Without that, all of our hyperplanes are going to go through the origin 0, 0 if it's a two-dimensional one, or 0, 0, whatever number of dimensions that we have when we have that. So we'll need also to add in x0, theta 0, okay? Which is going to be multiplied for every dimension by a unit observation of 1, just so that we can vary it, okay? All right, so we're all good there. And so what we're doing with most linear classifiers is we're just going to find this hyperplane and then decide which way the hyperplane is facing, you know, so that we can classify one direction as positive and another one as negative, right? And it's very easy. If the norm is facing, you know, a certain direction, then the values that are above that threshold are positive ones, and below that threshold, as it says here, are then negative ones, okay? So after that, well, we've gone through this, right? And basically this allows us to separate cleanly any data sets that are linearly separable. And you guys had some practice with that in your collab notebooks, okay? And so this diagram confuses a lot of people, but it's actually not so complex. So just let's center in over here, okay? So what we're saying is that PLA, sort of like concept learning, only cares about certain types of examples. Here, PLA only cares about misclassified examples because those are the ones that we want to get correct, okay? And we're just going to move the classification hyperplane to help with that, right? And the only thing we need to do is then try to perturb the hyperplane in some way to make sure that the hyperplane weights get tuned so to get this thing correct or not, okay? So for example, let's say our hyperplane is right down the middle here, okay? And we have a vector that lands on this side, okay? It's a positive instance, right? That's what it says over here. But it's classified incorrectly, right? When we take our theta and we times it by this, we actually end up somewhere over here, okay? So it's in the wrong category. It's going to be classified as negative, okay? And by this diagram, what we can see is that when we just add the weight vector to the actual observation vector, then we get this particular guy here, right? So we're going to end up with a new set of weights here, which is going to hopefully place that particular point in the right place, in the right side of the hyperplane, okay? And the same is true on the reverse, right? So we have the reverse down here. We just switched the colors around. So here it was classified in the wrong direction, okay, was classified over here. And then we're going to take the negative of this vector and add it in, okay, because we have a negative sign. So we just collapse both cases as you saw, okay, and then we're going to end up with the point on hopefully the right side of the hyperplane again, somewhere over here. Okay, so that's the idea that we have so far. And, if you get this idea, maybe I'm going to ask you a quick poll question, all right? So with this correction, when we multiply, okay, when we multiply the sign of the correct answer times the observation vector, right, our data instance, and we update our weights to this new theta, okay, are we guaranteed to get that instance correct? Yes or no, okay? So this is your chance in this help session to participate. So you go to your participation buttons, yes or no, and you can give me an answer. If you're not sure, it's okay. You can just try your best. I'll let that sit there for a minute. You guys can chat as well. So if you have it on chat, then you can say it. Okay, so Akansha asked me again, okay, what is the question actually that I'm asking? Okay, what I'm asking is, we're doing this weight update, right? We're doing this weight update. We're taking the original weight vector, right? And we're going to change the weight vector by adding another vector to it, right? This is this vector that's over here, right? Or the one that's on this side, right? We're basically taking the original theta and permuting it a little bit so it's on the other side, right? Okay, let me see whether I can erase some of these things, okay? That actually works pretty well. Okay, so it's going to be an update. It's going to wiggle. In this case, for example, the original weight vector, it's going to wiggle it so it's facing this direction instead, okay? And in this case, it gets it right. Okay, so a good third of you said, well, actually more than that, said yes, it looks like it's going to be corrected. In this case, it is corrected on these particular examples that I'm showing here on the right. But unfortunately, it's not guaranteed, okay? So you can imagine, for example, if I took this case, all right, and I made the x vector observation a little shorter, maybe like that, okay? And then when I add yx times x, yi times xi, I'm just going to add a vector like this, okay? So you can see where my theta prime ends up is actually somewhere around here, okay? This is my new theta prime. Let's say theta double prime, okay? Whatever, okay? The whole point is that when we are updating our weight vector, we are getting closer to getting this thing correct. And sometimes we might overshoot. Like if our x vector was really long, okay, we might totally move it to the other side, right? That's also possible, okay? But it is only guaranteed to help move that instance in the proper direction, okay? It's not guaranteed to correct it. So although those lecture slides are trying to give you a very simple idea of this, okay, it doesn't solve the problem directly, okay? Of course, in the limit, the problem will get solved. We saw that in the perceptron proof, okay, that basically we can cap lower bound and upper bound the number of updates that we need to get all of the points correct. If, again, the case is the data is linearly separable. Are you guys all good with that? If you are, let me know. If you're still a little confused, we can try to explain it one more time, no problem. Okay? All right, so that's one thing you should remember is the perceptron learning algorithm as it is originally conceived does not necessarily correct a misclassified point on the first try. Okay, now it could select the same misclassified point again and then update it again and again and again until gradually this theta vector points more and more until it gets to the other side. And that's the whole point, right? We're going to wiggle it until it updates. And now some of you might also think, well, it makes a lot of sense to actually try to multiply this x vector times yi, but make it so that it actually moves across this boundary, right? Because this is our classification hyperplane boundary, right? If we did that, then we would make sure that we actually correct the misclassification. And that's fine too. You could do that as well, okay? It's not the vanilla perceptron learning algorithm. It still has the same type of guarantees for convergence, okay? It just takes maybe a little shorter, but a little bit more computation on the scaling values. Okay, so hopefully we're all good with that. You understand that the perceptron learning algorithm actually does correct the misclassification, but not necessarily on its first try. Okay, great. All right, let's go. So let's see. I'm going to try and hope for the best here and see whether I can get this to slide share. See, 5. Nope. Okay. Well, anyways, all right. I still don't know how to work this laptop very well. Okay, so anyways, PLA continues to run, right? We're going to always pick a misclassified point. We're going to just change it up by doing this type of work, all right? By finding a misclassified point, updating the weight vector by taking the class, timesing it by the weight vector and getting an update, all right? We're going to do that until convergence. Okay, so you can see through all the slides that we're updating and we're picking a misclassified point and we're moving around appropriately. Okay, so you already know what happens if the perceptron can't fit the data. It's not going to find a separator. It'll keep on trying, but it won't find one. Okay. So when we go to linear models, basically the perceptron algorithm is one case, right? It's a case of one of the classification algorithms that we've studied. Okay, we've studied other ones that are not linear models, like naive Bayes, like KNN. Okay, but when we come to the linear models that are all dealing with something like a signal, right? Whatever the signal is, which is basically some way of taking the weights and timesing them by components in the X, we get the signal, all right? And then we have several different ways of dealing with it. Classification just says, is it above or below a threshold, right? Regression says, what's the actual value of the signal? Is it a positive number or a negative number? But it's going to be a number in the real valued line, right? So that's called regression. Okay, logistic regression, we're going to cap this regression value, this signal, okay, this thing over here, but we're going to assign it some other numeric value. We're going to scale it to an interval between 0 and 1, not inclusive, so that we can get a probability estimate out of that, okay? So we saw all of these here, right? So we'll just skip that around. And we'll go through the pocket algorithm. Pocket is very simple, right? We just keep the best hyperplane and it doesn't take a lot of space, right? It just takes a little tiny bit of space to save the number of parameters, right? We need to keep 2 copies of weights, right? The best set of weights and the current set of weights, okay? And then we can update from there appropriately, right? So you can see how it works. You can also, if you're thinking a little bit ahead, all right, thinking about what might be on tests and things of this sort, think about variations of these algorithms. So Pocket is a simple variation on PLA. It keeps one best algorithm, one best set of weights, but what happens if you were to change that? What happens if you had, let's say, have 2 best sets of weights or n best set of weights, okay? And maybe you want to restart in different places, okay? After a certain number of iterations, it's not converging, maybe you want to go back, okay? And you can think about algorithms to do that type of work. Okay, those are all other ways of optimizing. Of course, they don't have the same type of guarantees as what we would have in perceptron learning. Okay, great. All right, so then we'll go on. So we'll go on to linear regression. So linear regression is actually, again, very simple. We're just taking the transpose of the weights, right, timesing them as a dot product against the X. So we have the same type of signal as we saw before, right? And the way that we do this type of linear regression is to use this idea of a squared error. So you've seen this many times. The intuition is very simple, right? That we think that when we have large values that are off by a lot, those are pretty unacceptable. So what we want to do is try to minimize their square rather than use a linear sum, okay? So large errors count disproportionately more by their square, and then we're trying to find a good fit that's going to keep all of the square errors as small as possible. Okay, so it is basically, as we saw already, some type of pointwise um, categorization of costs, just like everything else that you're going to see in this course. Okay, we don't believe that any of the instances interact with each other, so that's why it's just a simple average. Okay, so make sure we're clear about how linear regression looks like, right? So we have a hypothesis X, and we have a real value. Okay, so here's an actual observation. This is my correct value of this particular point. So I have this X value, and it's supposed to regress to this Y value. But my actual hyperplane says it regresses to this value over here, right? So there is this error, okay, from Y. So I'm measuring the distance between my actual Y value and my regress Y value, okay? When you get to things like SVM, you'll see that the SVM actually measures in a different way, right? So here we're in the SVMs that we're introducing this week, we measure to the perpendicular of the hyperplane, okay? But here we're just talking about loss for individual instances, and here it's just the difference between the actual Y value, or my F hat, and my predicted Y value, or my F, or sometimes we'll denote it as H, okay? So these are vertical bars on our Y axis, okay? So they're always going to look like this in any higher dimensional space, okay? So in logistic regression, we are still using the signal, okay, this signal here, right? But we're going to compend it. We're going to put it through another function so that we can map all of these real values from negative infinity to positive infinity into an interval, a fixed interval between 1 and 0, okay? So that's what we're going to do, right? So we already said before, this is the sigmoid function. It's basically got two terms, right? An exponent of the signal divided by 1 plus the exponent of the signal. And you can play around with this. Again, if this exponent of the signal gets very large or very negative, then we're collapsing into two values, right? Either close to a 1 or close to a 0. If both of these terms are basically 0, basically 1, sorry, and because my S might be a 0, right? If I have S of 0, then I have e to the 0 over e to the 0, sorry, plus 1. And then this is going to be 1 over 2, and that will be right here in the middle, right? So we're getting the case where there's no signal, it's neither positive or negative. We're going to interpret that as a 50% probability of being positive or negative, right? Sitting right on the fence, right? And as we get closer, a much more positive value, we're just going to dampen it out. This is an exponentially decaying curve, so it tapers off as we go closer to 1, to say it's much more likely that it's a positive case when I have a very strong signal in the positive direction. Okay, so here, let's be careful that we are thinking about a probabilistic interpretation of this. All we're doing is we're mapping the information of the real line value into an interval between 0 and 1. And actually, how we do that mapping isn't important, okay? It just has to fit in that interval. So there are different types of sigmoid functions rather than just a logistic function. You'll see one later in the neural network lecture where we talk about hyperbolic tangent, okay? That's the same type of idea. It's curved a little differently, but it's offset a bit more down, okay? But for all intents and purposes, the only thing that we need out of this function is to take the real valued line and then map it to an interval between 1 and 0. Of course, we couldn't use a linear function to do that, right? Because a linear function, there's no way you can squish positive infinity and negative infinity into something like 1. We have to have some type of gradual decay for some part of the function, okay? So I hope that's all clear, okay? So again, when we think about this, the labels that we're trying to get for logistic regression are binary labels, all right? But the outputs that we have we are just going to interpret probabilistically, okay? Again, whether you believe that it's 57% or 90%, it really doesn't matter. What we're just trying to do is get this intuition that things that are uncertain are closer to 50%, and things that are highly certain are closer to 0 or 100%. Either direction is fine, okay? So again, when we think about logistic regression, we have to have the right type of loss, okay? Because our loss has to deal with the label. The labels are binary, okay? So did they have a heart attack or not? That's only a 1 or a 0 decision, okay? Whether you observe that event or not. Okay, you can't observe, let's say, a 60% probability of having a heart attack. Okay, it's just not possible, right? Either event occurs or it doesn't. So when we get to the loss optimization, then we have to cater for that. Okay, this is why when we use linear regression, we try to use it for classification by saying, hey, well, if the sign is positive, it's got to be a good thing. It's a positive case. And if it's negative, we have a negative case, right? That won't work very well for classification because, again, we are going to measure squared error for linear regression. And in logistic regression, that's not what we're doing at all, right? Okay. So the cost function for logistic regression looks like this, right? We're just taking this exponent, right? It's actually not going to have a closed form solution as we're going to see in the second half of the lecture for the case of squared error, right? Squared error actually has a very nice decomposition. It's both a plausible error or cost metric, as well as one that's mathematically convenient for us, okay? And so when we have squared error, it's nice for linear regression, but for logistic regression, we don't have that. And in a lot of cases, when we choose a loss function, we're not going to be able to compute a closed form solution, all right? We're going to need to iterate, going to train over epochs to try to tune the weight parameters to give a better value for our loss function, right? So to minimize loss so that we can get better classification outputs. Okay, so in gradient descent, I hope you get this idea that when we have a loss function, okay, what we want to do is think of it as some type of landscape, okay? A landscape that has maybe hopefully rolling hills rather than jagged mountains, okay? And the whole point here is that we want our cost function or our loss function to have some type of smoothness to it. Why? Because if we have a smooth thing, then we can take steps in a way that's going to help minimize it. If it's a very jagged landscape, you could end up with a lot of local minima and you wouldn't be able to figure out where to go. You sort of have to restart and then try again. Okay, so if we have a smooth landscape, that's good because we can take the derivative, and in some cases we can take the second derivative to find a stationary point and then check whether that's a minimum or maximum. Okay, but for most of the types of loss functions that we look at, we just look for a derivative, right? That's going to give us a gradient, right? A derivative is for one dimension. But when we think about a gradient, it's just a case where we have partial derivatives in several different dimensions, okay? So here's where you have to have a good understanding of the linear algebra parts, right? So each component of x, right? So we have all of these components of x, okay? All right, x1, x2, all the way to xn, okay? They're all in their separate dimensions, okay? So we can think of, let's say, a two-dimensional landscape, okay? And then, it's got some points in it or some space, all right? And what we're doing is we're starting with some value of these, okay? But there's not actually our x. Let me erase that, okay? These are actually our thetas, okay? So the weights attached to these two things, right? So we have a corresponding theta 1, theta 2, theta n, right? And all we're doing is saying, okay, well, we're starting with whatever our initial theta value is, okay? So this is our vector theta, and I want to update this vector, okay, by doing something. And how do I do it? Well, what I'm going to do is I'm going to do the partial derivative for each of these, okay, without considering them in tandem, okay? So I'm going to look at, let's say, just this side, right? I'm going to have my eyeball over here, right? And so this is supposed to be an eye, okay? So I'm looking at this landscape just from the front, okay? Just from the front, okay? And I'm asking myself, if I look at this thing from the front, maybe, let's see, let's change the color here. Let's see whether that works. Okay, if I look at it just from the front, it might look like something like this, okay? And so like this peak over here might be this one, etc. All right, so if I look at my current x theta 1 value, maybe it's like this one here, okay? So that's theta 1, okay? And what I'm doing is I'm taking the partial derivative of my loss function, this landscape that you can see over here. Okay, this landscape I can see over here, and just take the partial derivative with respect to theta 1. Okay, the loss function with respect to theta 1. And then that's going to give me the derivative of this particular point. Okay, how this particular function, okay, is changing at this point. Okay, so at this point it looks like, oh, maybe, it's sloping a little bit that way. So the right thing to do is take a step in that direction. So I'm going to go a little bit in this direction. Okay, that's the idea. Okay, but I'm not doing it in a single dimension. I'm doing it over all n dimensions. Okay, so if you just imagine for a second, I only have um, two features, an x1 and an x2 with weights theta 1 and theta 2. Okay, so just looking at this part here, then basically what I want to do is take a step in this direction for theta 1. Okay, and then when I'm looking from this side over here, right, here's my eyeball looking at theta 2, maybe from this side, the landscape looks a little bit like this, okay? And let's pretend we're over here for theta 2. Then the partial derivative of the cost function for theta 2 is telling the gradient is going up like this. Therefore, I want to minimize. I want to flip that around. I want to go a step in negative direction here, okay? So what does this mean? That means every time we're doing an iteration, when we're updating our weights, we're doing something like perceptron learning algorithm, where we're just updating one component of my weight vector using a partial derivative, right? So I'm going to do the partial with respect to theta 1. I'm going to do the partial with respect to theta 2. And then do the partial of this with respect to theta n, right? So this is actually the wrong way. I should write partial j over partial n, right? So this is my cost function, right? I'm taking the partial derivative of my cost function with respect to each of these individual parameters and try to figure out where to go from there, okay? So that's what the vector notation is supposed to give you, okay? So in any case, when we do this, right, we're going to get this idea of a cost function, right? And like I just drew, we can think about a cost function that has some type of landscape. So here in this landscape, we might be looking at some minimum value over here, right? So if you think about this in terms of this theta 0 and theta 1, it might be some type of bowl shape, right? Something like this, okay? All right, and we're starting and like each of these contours here has the same cost amount, okay? It means that the cost value for any set of parameters on this ellipse, okay? This ellipse out here, or this ellipse, this green ellipse out here, has the same amount of cost, right? So if we're standing anywhere on this lip of this cost bowl, the gradient is going to be pointing upwards out of the bowl, and we want to take the gradient step going downwards, right? We always take the negative of the gradient so that we can step in the right direction, okay? And again, each of these gradient steps is being partially differentiated. So when I think of this theta 0 here and this theta 1, and I'm, let's say, looking at this point right over here, okay? Let's see, okay? Then when I look at theta 1, okay, I can see at this point, the cost is going up if I go this direction. So I'm going to walk this way down, okay? And then for theta 0, which is below, right? I can see the cost is going up here. So I'm going to take a step in this direction, okay? And actually, when we do all these partial derivatives together, we get the final answer, right? So we're going to end up with a vector like this and step towards that direction, okay? Okay, so it's actually going to be, in this case, the normal to this ellipse, right? Because everything on this ellipse has the same cost. So it's going to be the norm of this, right? So here's the gradient going up, and we're going to follow the gradient down in this direction. Okay, so again, if you understood that and you feel a little bit more comfortable with the vector math, please let me know. If you're still really confused and I have made it worse for you, please let me know either in chat or in the yes, no. Okay, so I'm going to zoom out here for a minute here. Okay. You guys all still there? Everyone with me? Okay. Okay, 1 or 2 people. A lot of people tuned out. No worries. This is a help session. If you're being helped, good. If you're not, then engage us in another way. Okay. Thank you, Jonathan, Joseph, Kathy, Crystal, and Yu Chen, and many others who I didn't get a chance to see. Okay. Great. So I hope that makes you feel a little bit more comfortable. All we're doing is taking partial derivatives and just adding all these partial derivatives up because again, in 2 dimension, you can sort of visualize it. But when you get to 1,000 dimensions, it's a little bit messy, right? You can't really visualize it. All you can think about is for each of these 1,000 dimensions, we're solving a 1D problem, but 1,000 times, right? Just simultaneously. So they're all partial derivatives. Okay. Let's go on. Right? So we can imagine it is the case of gradient descent. What we are going to do here is batch gradient descent, which is to basically say we're going to go through all the points, find the case where the cost function is minimized after all of the gradient for all of the points, okay? This partial derivative over all of the different examples. And then when we have that, we're golden. We know exactly which way to tune each of our partial derivatives to take the step that's going to update our weights, just like in PLA, but do it in such a way that it's going to minimize the loss, right? Because that's what we're doing. We're minimizing loss. We're trying to get more classifications correct. Okay. So again, we can do it in any way we want. The way that we introduced in this part of the lecture is just with a fixed step size, all right? And we've already illustrated which direction that we're going to do. We're going to do that by going through all of the different instances, the entire data set of M instances, and then calculating the partial derivative for each of the components, then adding them all up, and then I have my vector v, right? And then I'm timesing it by some scalar, which is my mu here, and then I'm taking a step, I'm updating this. This should look exactly like what you did in perceptron learning algorithm, right? We're updating the weights by taking a vector times a step size, okay? Before, that step size was just y, right? Y equals either +1 or -1. Now we're saying maybe we can tune it, okay? And you can see where we're going with it because as soon as we did that, we said over here that we are going to take a variable step size. So I'm going to blow this up because it's sort of cool. All right. All right. So what we can see here is that when we take a normal step size, okay, just like don't think about the gradient, we could have problems. We could take things that are too small and it's going to be very tedious to get to the right amount. We could do things that are too big and we'll just ping pong around in this cone and never actually reach the bottom, okay? Or we can take a variable step size. And this is sort of intuitive, right? If you want to get down as fast as possible, as soon as you see a very steep slope going down on a hill, like say you're at Bukatima, right? Then you just go down, right? You can take a long step to go as far down as possible. But when you reach, let's say a plateau, right? Let's say you're somewhere over here, okay? Then you have an idea about the gradient. You know, you can see that it's a little slope down this way, okay? But maybe you don't trust yourself because it's a little foggy, okay? You just take a little bit of a step, okay? And then you reassess your idea. You take, again, a poll of all of the points and say, which way is down, okay? And then I'm gonna take another small step. So when it's very clear that we're going down steeply, then we would take a large step, right? So you can see here, there's a large step. You can see this line segment is very long, but over here, there are a whole bunch of points in between. That means there's only a very tiny line segment between that, right? So again, variable step size is a good thing, right? It basically says, I'm going to take a big step when it's very clear the gradient is pointing a specific direction to minimize loss, okay? And when there's not such a clear signal, I take a small step and reassess. Okay. So that's what we're doing with varying the step size, and we get the final logistic regression algorithm. And actually, this type of gradient descent is useful for any type of smooth function, as you probably saw on the earlier slides. And so can we actually use this for linear regression, even though we have a closed form. What do you guys think? If you think so, then give me a yes. Otherwise, tell me no. We always should use the normal equation. Okay, so you can do it in chat. Again, you can do it with the yes or no. Okay, so hopefully you guys all got the idea that as soon as you use a linear regression or logistic regression or any type of algorithm that admits some type of derivative, okay, of the cost function that is smooth, all right, meaning we can calculate the gradient, then we know which way we can step, right? Because the gradient basically is, a set of partial derivatives that tells for each dimension which way is the way down, right? Which way for this function on expressed for this particular coordinate value is a good way to minimize that cost function, right? So we can use it both for linear regression, we can use it for logistic regression, we can use it for pretty much any loss function that is smooth and continuous, okay, in the first derivative. Okay, now there are some times that we'll use the case of using the normal function that we'll see in the post lecture. Okay, I don't think we're going to step through all the math there unless you really want to. Okay, but the whole point is that we've got two choices for linear regression. We can use the normal equation, which basically doesn't take any iteration at all. It's a closed form solution. You just calculate it and bang, you are done. You have the solution for linear regression. That means for a set of points, okay, I know right away, without any extra work, that I have a line that's going to minimize all of the squared errors. I don't have to perturb it, move it around, all of this funny stuff that we do in PLA, okay? With logistic regression, with linear regression, with squared error, we can find a closed form solution, and that's using the pseudo inverse, right? Now, there are times which you might say, well, the pseudo inverse is so great. Why don't we use it all the time, right? Because I don't need to do all this fancy iteration stuff where I move the hyperplane, tilt it left and right, etc., as we did in PLA, as we're doing in logistic regression. Why would I do that for linear regression? Because I can do it in one shot. Okay, does anyone know why we would do that? Okay, so I'd like you to think about it because it's a key point, okay? Even though we have a closed form for solution for linear regression, often we don't bother to use it. And it's you can think about why. And when we get to the point of having big data around, nobody uses it, okay? Why? Okay, there is a specific operation that needs to be done in linear regression to solve it in a closed form solution, okay? And that particular mathematical operation is expensive, okay? So I want you to think about what that is when we come to that, okay? So we've actually finished this part of the lecture, and I'm just going to hopefully, run through a little bit of the second half, okay? So yeah, all right. So I see there aren't that many questions, so I'm just going to continue to go through. I think we only have 13 questions so far, so we'll go ahead and answer those after the second half. All right, so we can get to more of the lecture. Okay, all right. So let's go. Let me get this out of the way. All right. So, we are studying linear algorithms because they are really, really important, okay? It seems like very limiting to study them because they can only make straight lines, right? But what we're saying with nonlinear mapping is like, hey, it doesn't matter whether we're painting straight lines or not. We can just pre-process the input, right? Do something with the inputs in such a way that then we have features that are linearly separable. We have data points that are linearly separable, right? So we might have something like this, right? On the left-hand side, we have a whole bunch of points. It's really easy to see for us in 2D that there's a cluster here. But if we're using linear models, we have to only draw lines, right? And we saw this in the XOR case. We can only draw a line like that, or like that, or like that. But it's clearly not going to get everything right. Right? If we are able to allow to join 4 lines together, maybe we can get it correct, that's called ensembling, taking several different classifiers and then using them in a voting system or something like that to get this to work. You're going to see this in decision trees in week, I think, 10 or so. Okay, but for now, let's just pretend we only have one line. Okay, so if we only have one line, it's not going to work. What we'd like to do is bend that line to look a little bit like that. Okay, how can we do it? Well, we can't, right? All that we can do is use a linear classifier, but we can play with the data beforehand. Let's pretend that we just took the data and we moved it around, okay? We moved it around a little bit, okay? And we transformed all of these blue points to sit in another space, okay? So we're just gonna put them over here. And we took all of these, for example, and found a way to map them over here. And we might do that by using some type of nonlinear mapping function, or phi, or phi if you prefer, okay? So this phi is going to take these coordinate values, okay, our original x, okay? My original x, again, has all n attributes, okay? And all that I'm going to do with this is then square all of the coordinates, okay? So now my new x1 is just x1 squared. My new x2 is just x2 squared. My new x3 is x3 squared, okay? And then I can get all of them over here because basically I've taken out all negative values. You can see it starts from 0 and 0, right? So I've just basically drew the distance from the origin here on each of these x1 and x2 coordinates, and I plotted it here, okay? So basically, when I look at this, when I draw a straight line here, if it's a straight line like that, it might represent a circle or an ellipse in the original space, right? Okay, everyone pretty okay with that, right? Because what's happening here is we are tricking the linear classifier. What does the linear classifier get to see? Right? Does it get to see what's on the left side or the right side of this diagram? It has no idea of this, okay? It's completely gone. All it sees is the thing on the right. Why? Because you introduced this phi function beforehand, before passing the data to the linear classifier. So even though originally it looks like this thing on the left, you went ahead, had some abstraction. That abstraction is called phi. That phi is going to take the data and just spit out another set of values, another set of vectors, and then I have something like the one on the right. Okay, and then this is nicely linearly separable. The linear classifier says, I know how to do that. I can do that. Okay, and it'll draw the straight line for you. All good, right? So it really doesn't matter how we do that, okay? As long as we can define some type of function that can preserve a linearity in the z space, in this coordinate space that the actual classifier gets to see, we're all golden, okay? So this is really nice, right? As long as we can find a phi function that can do this, then we can use a linear classifier, right? Problem solved, right? Wait, we still have to define what the phi function is. How do you find this stupid nonlinear mapping function, right? So it begs the question. You're just pushing the work off to another problem, right? So that's the crux of it, right? So the whole point is that here we are going to say, let us still use linear classifiers. Okay, we're going to separate the problem of finding good features, okay, whatever they might be, okay, from the raw features. Our raw features are our original data, okay? And our job is now to take that original data and do something smart with it so that we can get features that are going to be linearly separable. We already saw a case of that, right? What was that? The MNIST digits, right? We said we have all these 64 points, okay? They're all in gray values, so they've got values from 0 to 256, okay? Or 2 and 0 and 255. Let's stick with the computer science notation here, okay? And then what did we do? We said, I don't care about all of that. We are just going to use this particular idea of transforming it into symmetry and vertical symmetry as well as saturation, like how many parts, how many dots there are that are black, right? So eights happen to have more graphite on the page. So we can say if it's an 8, it's probably going to be darker, right? Great. Okay, so Ching Han asked, how do we select these nonlinear functions? Okay, yeah, well, that's the problem. That's what your job is as a machine learning engineer. Or if you believe in the current deep learning stuff that we are going to teach you in the next half, or hopefully you've already started to investigate, or maybe you've actually played around with it yourself. The idea of deep learning is, uh, it's a learning problem to decide what this phi function is. So you just give me the data and I'll try to engineer it for you, okay? But most types of machine learning need some data analysis, okay? This is what we're going for in your project, okay? Which is to say, you as a scientist, you as a machine learning engineer, you as somebody who respects and understands the data, needs to think about what that data represents, okay? If it's a string of numbers that is 1,444,000 long, and they're all values between 0 and 255, okay, maybe it represents a picture, okay? If you didn't know any better and you just told me it's a bunch of numbers, I wouldn't know what to do with it, right? But because you have some perception about what those numbers mean, they form an image. There's certain semantics with respect to this set of numbers because they're all in one place, okay? Or this set of numbers because they all represent an edge or a type of texture, okay? Then we can try to use this intuition to engineer this magic phi function. Okay, once we have a phi function, hopefully we can get it into a case where we have features that are meaningfully separating and semantically intuitive. Then hopefully we have it in a space where it is linearly separable, right? So when we have it in a linearly separable space, we can draw a hyperplane, right? And that hyperplane is in my Z space. So this is what the classifier sees, but we only get to see the pixel values, right? So we see this grid of images or, some other type of loan application, etc. Those are in our original data space, right? Okay. So when we do the inverse, right, when we've classified a new point, let's say we took this point here and we classified it, then we have to ask ourselves, how did the phi function move this thing here? If I map it through the inverse of the phi function, maybe it lands somewhere over here. So now I know that thing is actually a red point. Okay? All good. Okay, so we think about all of the things that are being done, right? We take our x's, we transform to a z, we then classify in the z space. We actually don't have thetas in our x space because all of the work is being done in our z space, right? We're just, we've got a mechanical Turk hidden in a box. That box has, a slot to put in data, and out comes a linear hyperplane, and then we can stick new points in there, and the new points come back with a label, right? So that thing happens inside the magic box in our Z space, right? So that's what happens there, okay? So hopefully you get this idea of the case for a nonlinear mapping. So it's sort of like a good thing, but also sort of like anticlimactic, right? You're saying that, okay, we can use linear classifiers, but we're going to push all of the work in finding a hyperplane off to a phi function, which I haven't disclosed how to get, okay? So for many years, pre-deep learning, about from 2008 all the way before, people had to spend a lot of time thinking of good things to use as features. I'm a person who does natural language processing research. So here we were thinking about, what's the class of words, how the words interact with each other, how can we look at agreements between, let's say, nouns and verbs, etc. All of those things we try to engineer as features in this Z space, right? The Z space is then where we are going to use a classifier to do all of the work, okay? All right, so the other half of this that we wanted to go through for linear regression was the normal equation, right? So the normal equation is just basically saying that if we're using squared error, we have a closed form way of coming up with the solution, okay? So I'm not gonna go through all of this because I think unless you have specific questions, we can do that. And I think you have questions there, okay? But the thing that you need to realize is that this contains a very hairy operation, okay? It contains this thing here. Okay, that is an inverse. Okay, so Leslie already put there time complexity, right? So that is the key problem. If we're going to take this matrix, okay, this one over here, right? And we need to invert it, okay? That takes cubic time, right? Is an order n cubed operation, okay? So you can imagine how big this thing is, okay? So how big is that? All right. Well, it's n plus 1 times n plus 1. Okay. Not so bad, right? But it depends on what type of data you have, right? If you have lots and lots and lots and lots and lots of examples, okay, but the individual x observations are not so big, right? Because the defining characteristic of this matrix is n, right? The size of the observation, okay, the instance. Then we're not so bad because our m's that we depend on are out here, right? Okay. But if we have a very large amount of data, let's say an image, right? Then I have to do this inverse of, let's say, 1.44 million uh, integers, right, for a particular image. That's crazy. You know, you got cubic time here. I don't want to do that, okay? So that's why many times we don't use the normal equation for linear regression, okay? So you can summarize it as this, you know, if my x vector is pretty short, okay, then it's probably okay to invoke this. Okay, we can use the normal equation, all right? But when we get to big data and you have many, very long way of characterizing a particular instance, like you want to decide what movie to watch and you have the entire history of what you've listened to on Spotify or all the things that you watched on Netscape, or maybe you use a lot of e-commerce and you have lots of transactions on Lazada or Shopee, right? Then it becomes, this thing is not short anymore, it's long, right? So as soon as it's long, it's not okay. You know, it's going to take a lot of computation to get this. And I can approximate this and iterate this in ways that might be a little faster. Okay, so that's what I want to do instead. Okay, so we've answered this. There's also a question about that. You know, if we don't have a full rank matrix, the inverse of x transpose x might not work, right? We might not be able to do that. Okay. So here's the crux of the problem. It's a cubic operation that we need to do. Okay, so we're all good with that. Okay, one common problem that people have is figuring out why can't we use linear regression for classification, okay? And I'm gonna go over this very quickly. Again, what you can see here is a whole bunch of points, okay? And where would we actually want to set the boundary, okay? So this is the case where we use linear regression to set the boundary. Okay, so after we've optimized for squared error, okay, we got the points here. Okay, so is this a good classification boundary? Well, it's not bad, right? But it could be a lot better. You can see there's a whole bunch of blue points here that are being missed. Okay, the better algorithm would have been, you know, maybe I could have made the hyperplane a little bit more aggressive, right? I would have gotten a couple more red ones wrong, okay? But this whole slew of blue in the middle here would have been correct. So from an accuracy standpoint for binary classification, this other lighter black line that I drew is a better boundary. Now, why didn't linear regression get that? Okay, why wouldn't have linear regression got that boundary? Well, like I said, it has to do with this idea of squared error, right? Linear regression is saying transgressions that are very far away from the line are not good for me. Okay, so that's what I'm doing. So why would it be the case that if I moved something over a little bit more this way, okay, that I would get more squared error? Okay, so you can think about that. All right, so there will be cases in which the misclassified ones, like this one over here and this one over here, are actually going to get worse, okay, because of this squared error picture. Okay, we're going to tune things in such a way that we get less squared error, but our binary classification is still worse than in the case for using logistic regression, okay? Because we have all of these outliers, right? Outliers that are far away from the decision boundary, and they're going to matter a lot more. They're going to matter disproportionately more. And that was the whole idea of using linear regression in the first place, right? Is that we don't want large errors. We can accept lots of small errors, but not large errors. But when we're doing classification, because it's binary, we don't care whether you got it off by a little bit or off by a lot. It's just off, okay? So it's wrong. So we want to minimize the number of cases which we get wrong. So squared error has no business dealing with classification, okay? And this is why when we do classification, we need to use the right way to use the signal, okay? So that's why we have logistic regression, right? So we're interpreting it as a probability of being wrong, not as a somehow weight that's going to push things for getting right or wrong, okay? So I hope you got all of that. I think it was a little bit more clear in the lecture as I got to edit it a couple times, but in any case, we can go on from there, okay? So another really cool thing that everyone in the class should really understand is the difference between batch and stochastic gradient descent. Okay, what's the difference? Absolutely nothing, okay, in the long run, okay? Why is that, okay? So when we think about doing gradient descent, right, what we are doing is, again, finding this landscape, okay, and then trying to find a minimum. So we want to go somewhere here or somewhere here, right? And so what we want to do is actually iterate through all of the different points, right? This is what it says here, right? So I'm going to get the gradient of the loss. And to do that, I have to find the pointwise cost, right? And I'm going to find the gradient of this by taking the partial derivative of this versus all of the different parameters that I have, right? Okay, so I'm going to do all of that. And then in order to find the actual gradient, I have to do it all over all m points. Okay, so like it says, this J train is based on all examples in my entire data matrix. That means this entire big thing, whatever it is, I have to iterate through all of these guys here, okay, to compute that one gradient, okay, my delta, okay, that I'm going to use, sorry, this is the wrong symbol, right? Our nabla of J, so that we can decide which way to step, okay? That seems like a lot of computation for one step, right? And we said already that if the step is clear, going down very fast, then I take a larger step. That was due to our mu, right? So we said we're going to take this in proportion to whatever our vector is. That was what we saw in the pre-lecture, right? So if it's a vector, the gradient is very closely following down, then we would take a larger step, okay? So that was before, okay? Now what we want to do is say, you know what? Let's skip all this nonsense. We're going to calculate the gradient, but we're only going to do it based on a single point of data, okay? So I'm going to go through my entire data set, okay? And I'm going to choose one point, okay, randomly. So I choose U, okay? This particular X, I'm going to get the gradient of the loss function with respect to just one data point, okay? So that's easy. I take the partial derivative, but I don't have to do it over all the data points. I just do it over one, and then I get the gradient for that, okay? I'm going to apply that gradient and take a step as like normal, okay? And then I'm going to do it again. So I'm going to go through the data set again, okay, and select another one. Maybe I choose this one. Okay, I choose U. I'm going to take the partial derivative against this new X and then take a step in this direction, okay? So why am I doing that? Why don't I do that? Because, you know, if I choose one data point, the step that I'm going to take to optimize the cost for that one data point will be good for that one data point, but it's not necessarily the right direction for the entire data set. This is exactly like what we did for PLA, right? PLA, we said, find a misclassified example and then try to correct the vector for it. I don't care which one, just take one, okay? When we were doing gradient descent before, in the batch gradient descent case, we said, take every point find the correct direction to step in, and then take a step. Okay? What we're doing is an approximation, right? We say that over the average point, okay, the average point, our expected point that we choose, okay, when we do all of the math out of the way, okay, and we take enough of these steps, even if they're off for each individual point, they're all not stepping in the correct direction, but they're going to average out. These things cancel each other, and we get back the original gradient for the entire data set. Okay, that's what we're doing with this. Okay, so you can see how it works. It's more easily intuited from this slide. Okay, if we use gradient descent, okay, what we're doing is what's on the left side. Okay, it says I am currently at this set of weights, theta. All right, I'm going to look at all of the data points. Okay, calculate the gradient, and the gradient tells me the right direction to go is downwards this way. Okay, I actually know what this local place looks like because I calculated the gradient with respect to every point in my data set. Okay, but I needed to do that by stepping through all of the points. Okay, on the other hand, when I do gradient descent, but I do it stochastically, I actually don't see this landscape that I've painted for you. I don't see it. I don't see this blue, orange, yellow, whatever. Okay, what I see is an approximate gradient, okay, due to a single point. Okay, and that single point tells me that the direction for this case here happens to be pretty similar. Okay, for that for whatever point I picked at this particular setting of theta. So I selected one point. Okay, the point has the best gradient going in this direction, and I'm stepping this way. Okay, well, if I pick a good point, that's great. If I pick a bad point, I could go on off in another direction. Like, for example, if I was here, but I picked a different point, maybe the gradient would be pointing this way, okay? And then I would take a step in this direction, okay? So you can say, oh, that looks pretty bad. You're not going the right way anymore, Min. You're going off track, right? I say, never mind. It'll all work out in the end. I'm just going to take lots and lots of steps, and sooner or later, I'm going to reach the bottom. And I would be right, okay? That's what the math showed you on the last slide, that when I take enough of these steps, okay, over the expectation of all of the points, the gradient for all of the points will average out to the actual gradient of the entire data set, okay? So you can see the difference between what we're doing on the left side over here, which is basically a very, very smooth curve, right? It's just a little bit has straight line segments because we're taking a big step when we are having a strong gradient, right? But on the right-hand side here, it's pretty chaotic, right? Sometimes we're going up, sometimes we're going down, sometimes we go back where we came from, okay? It doesn't matter, okay? The whole point is like this type of calculation is much less expensive, and because of that, I can afford to do many steps, okay? That's the idea of stochastic gradient descent. Okay, so we can think of it on this case of 10 points, right? If I needed to calculate a gradient for 10 points, okay, and I took 10 steps, that means I had to calculate the partial derivatives for each time for 10 steps. So this is going to be 10 times 10, or 100 computations, okay? If I take 30 steps here, but I only have one computation each time, then this is going to cost 30, okay? So although this is a big cost savings over 100, you can see even though many times I stepped in the wrong direction, okay, overall, I'm still getting pretty close to where I want to go towards the end, okay? That's the idea, right? And the math is very simple, right? So let's try to get this back to the problem at the front. Okay, it's right here, okay? Because what we're just saying is when we take the average direction, that means the expectation of a single point's gradient, right? When we go over all of the expected points, then we're going to just write it out as this summation over all of the points. Then we're going to get back the same gradient as before, okay? Nice, right? So it just basically says, take lots of little small steps. Don't worry if they're wrong. you know, they will converge in the end if you believe in randomness and enough iterations. Okay, so everyone good with that? That's stochastic gradient descent. Okay, so we use this almost always. Now you can say, well, Min, wait, you know, using 1 point is not such a great idea, right? Because what happens is when you use 1 point, you could be going off in the wrong direction. But I don't want to do batch gradient descent either, because batch gradient descent, as you said, is already expensive. I need to use all m points. Can we choose something in the middle? And the answer is, what do you think? So I'm going to pause here for a second and ask you, can we use something between stochastic gradient descent with 1 point and batch gradient descent with m points? If you think so, give me a yes. If you don't think so, give me a no. Okay, I'm going to drink some water. Sorry about that. Excellent. You guys are really on the ball today. So what we do in many cases, especially in deep learning, is we use stochastic gradient descent, but with something called a mini batch. Okay, mini batch is the name for the collection of points that we want to use to calculate a gradient. Because as we said, okay, on the last slide, okay, this looks sort of messy, right? It's all over the place, okay? So if I took 2 points, or if I took 3 points, or I took 5 points, okay, any number, these jiggly lines over here would get less jiggly, right? Maybe we don't need all the points because all the points is expensive. Maybe we just want to use a few points to smooth things out, okay? You can think about the relation of this mini batch size to something like k and k nearest neighbors, right? We think that the single nearest neighbor is a little bit noisy. Maybe it's like a crazy neighbor, so I don't want it. Okay, so I take a vote of several things, right? So that's what we're doing here, okay? We're using this idea of a mini batch. Okay, so I'll just write that down, mini batch. Okay, and the mini batch we can set to some size. Many times in machine learning, we think about the computer architecture, how many points comfortably sit in a page of memory, if you guys are familiar with hardware limitations, okay? We calculate, we load all the points that can fit in a page of memory, we calculate the heck out of it to get a gradient, and then we save that gradient and say, okay, I got a good approximation. I'm gonna use this gradient to update my loss function, okay? So sometimes the mini batch is set to 64 or you know, some other nice power of 2 or even larger. Sometimes you get like something like 1024 or bigger, okay? Doesn't matter. The whole point is like how you set this is dependent on many cases your machine architecture because you just want it to fit in size in memory well, okay? And sometimes when you're doing it on a GPU, again, it depends on the size of the GPU, okay? So very good. So those of you who are following, Zhuang Yuan, Yu Chen, Yuan Hong, Yu Hui, and Li Shuo, and a couple others, thank you for telling me that you understand. Okay, so all that's good. Okay. All right. So we go to cross entropy. Okay, so some of you asked about the cross entropy. Okay, so here again, what we are trying to do is find a good idea of the likelihood of a point, right? So all we're doing here is using this sigmoid function, right? And we're using this sigmoid function to get a cost, right? So we're saying that we have our h, okay, which is the form of um, our classifier, right? It's just this thing here, which is the signal or theta transpose x, right? And we're just putting it through our function g, right? Some type of function. And this function happens to be the logistic function, okay? So we're just going to take this negative infinity to positive infinity, and we're going to squash it into something between 1 and 0. Okay, that's all we're doing. Okay, and we noted that actually, if you look at this, it has a nice form, right? The g of negative s, let's say whatever it is here, is actually the same as 1 minus the same thing here. So this distance here, this vertical distance, let me clean this up a little bit. Okay, so let's expand this bit. Okay, this distance here, okay, is the same as 1 minus this distance here, okay? So that's nice. So if I just take the negative of this, whatever it is, and then flip it on the other side, I have something that's symmetric, right? That's what the formula over here is telling me, okay? All right, so we'll go ahead. Let's see, what did I do? Okay, let's continue. Let's see, can I write? Yep, okay, good. Okay. So all that we're doing here is basically plugging this in. I'm going to say the P of y given x because we're using maximum likelihood here, as you guys have answered in the pre-notebook, right, is to say that I'm going to take this and then plug it in, right? So I've just taken this likelihood of all of the points, written it out, right? So I'm going to say these are independent samples of each other. So it's simply the probability of the label given each of the individual points, right, for my entire data set. Okay, so I get this, okay, all good. And so I'm going to step through this set of things that we're going to do, right? So if we do this, basically what we're saying is we want to maximize the likelihood of getting things right, okay? And that's easy. What I need to do is I can do anything I want. Maybe I can first introduce a logarithm just to make it convenient, because here the maximum and the minimum aren't affected by any type of scaling function, right? If I put a log or a natural log, the maximum will still remain the maximum, the minimum will still remain the minimum. So this is just a nice mathematical trick. Okay, so after I do that, then I can go ahead and move parts of the things around, right? I'm going to move this summation, this linear logarithm, natural log, sorry, inside of this multiplication, and that's going to transform it into a sum, right? So that's great. Now I have a sum. It's easier to work with. I don't have this multiplication or product, okay? And then I have this term here, right? And then what am I going to do? I'm going to switch it around a little bit, okay? I'm just going to change this to a minimization problem rather than a maximization problem. And that's easy. I can just change it to a minimum and then put a negative sign in front, okay? All good, right? Nothing special here, just going through the motion of getting things all set up. So I now have minimizing of a sum. This sum is over a natural logarithm of some function here, right? Whatever that g function is for. Okay, great. Oops. Okay, so then I'm going to continue on. I had to do it on the other side of the fence, right? So I'm going to take this g and then put it in this form, right? So how do I do that? Right, let's see what we did. We just took this g function and moved it downstairs, right? So that we take away this negative sign, right? So that gets dropped off here. Okay, hold on a second. Okay, so that all works out, okay? And then I have this part, right? What I want to do is take this g function and actually treat it with the understanding of the logistic function. So I've just plugged in what I know about the logistic function. This is my actual g of s, right? So I have this as my s. So I'm just going to plug it in here, right? So I have this yj transpose of theta times xj, right? And this is the s part. So I'm just going to substitute the s is here, right? And I'm going to end up with this. Okay, it's the same, right? We just took the inverse and then put it at the bottom and then canceled things out and we got this term. Okay, so hopefully you guys all see that. Okay, and so we end up with this form, right? This is our cross entropy error. Okay, so it just basically says what we want to do is to minimize this thing over all the points. So this is why we did the natural logarithm, is to take this product and make it into a sum. And this sum is very nice, right? Because this sum looks exactly like the ones that we've seen before, right? It's just something that is a sum over point-wise loss over individual instances, right? I don't have to worry about this nasty multiplication over here. I've transformed it into a single loss for a particular point. Okay. So that's basically it. This happens to be a nice smooth function, as you already know from looking at the loss function. So it has a nice iterative solution. It doesn't have a closed form solution like we do in the case of the normal algorithm. So we'll actually need to go through gradient descent, either stochastic gradient descent or batch gradient descent or a gradient descent with mini batches. Any one of those are fine. We're just going to iterate until we get to a plateau, right? And that's going to be the place where we're going to set our final set of thetas for our linear regression hyperplane boundary. Okay? All right, so I'm not going to step through the convergence thing because I think it takes a lot of time. But if you have any questions, let's go through some of these now, okay? So I'm going to pause for a minute and take a look at this. If you've got any questions that you want to mention out loud, please do just unmute your mic or turn on your camera and talk to me. It's always nice to see faces rather than empty names, right? Some of you I've actually corresponded with you through comments. Many of you have talked with your TAs, and that's good. Okay, but either way is fine. Okay, so let me just see whether I can make this bigger. I think I have to stop the presentation first to make it big. Yeah, okay. Okay, this one I think is really important. How do I get this to show up? Top responses, let's see. Nope. Okay, there used to be something, sometimes I can get it to work, sometimes I can't, to get it to show up as a, okay. I did click on it. Is it over here? Okay. Thanks, Leslie. I don't know why I can't do it. Okay. Anyways, I think I've gone through this part. Okay. If I didn't go through it to your satisfaction, please give me a chat or another message. Okay. So that we can go through it some more. Stop presenting. Nope, that is not the one. Okay. Let's see.